Eccoci qua. So last time, so a short summary of what we did last time. So what we are doing now is basically the following. It's trying to see what happens when I introduce interactions in my system, and how those interactions can be responsible for phase transition. And in particular, what we are looking for is a way to characterize what happens at the critical point. Okay, basically, the critical point, we saw it already in the case of the liquid gas phase transition. So now we are using a different model, which is this Ising model, that will provide also a critical point, and though the system is completely different with respect to a gas of particles obeying to the van der Waals equation. But actually the behavior close to the critical point are very similar. So those two systems have actually the very same behavior, and this is basically what is called universality, if you want. So the fact that different systems with different composition and interaction can behave in the same way at the critical point. So this is one of the main issue of this part of statistical mechanics. So the last time we did the Ising model in one dimension. The reason for doing the Ising model is that basically just a very simple model that provides already some insights in what's going on. In the case of one-dimensional Ising model, we can solve the problem analytically, so find the partition function analytically, and then derive everything from the partition function as usual. And what we saw is that there is no phase transition, there is no critical point, and the behavior is quite smooth. And the reason was that when looking at the free energy, basically in the free energy, what is more important, basically, when I change the configuration of my spin, is the product of T by the entropy. And even if I have a configuration in which the internal energy is not minimized, but the important thing is that it's minimize the free energy. Okay, and to minimize the free energy, I can do the following. I can both minimize the internal energy, or I can increase the entropy. Now, in the case of the one-dimensional Ising model, what is more important is the entropy contribution. And we did a short calculation. Well, we did the full analytical calculation. Also, we have presented an argument for explaining this feature. Now, in the case of the multidimensional Ising model, so now there is a full solution, analytical solution in the case d equal 2, which, however, we will not do because it's too long and too complicated. Now, what we did is to actually study the Ising model in a, let's say, arbitrary number of dimensions, but by using what is called a mean field approximation. The mean field approximation basically consists in neglecting the fluctuations of the spins, basically. And I think that we arrived last time at the free energy, the Helmholtz free energy, which was okay. This is of course usually as T log of the canonical partition function, and this is equal to minus kBt, and we have here minus beta and epsilon q m squared divided by 2, where I remind you that this epsilon and q, epsilon is the coupling between two spins, q is the number of closest spins, so the number of spins that interacts with each other, N is the magnetization, which which is defined as the derivative of the free energy with respect to the magnetic field, to this external field that, let's say, is similar to a magnetic field. And then there is another term which was M log. Then we have the 2 cos H of beta. Then we have H plus epsilon and Q, and that's it. Yeah. So I think that last time we arrived at this expression. Now the magnetization capital M is the minus the derivative of A with respect to H, and we have defined small m as the derivative minus the derivative of H per particle divided by A per particle divided by H. So what we just do here is to derive with respect to H this quantity. On the left hand side, so we divide by n, and so on the left hand side we just have m, no? Because when I do the derivative of this guy with respect to h, it by definition is n. And then on the other side, okay, by doing the calculation, so okay, this term does not contribute. I just have an h here, so you have 2 cos beta. Okay, maybe let's try it. You have a 2 cos h beta h plus m epsilon q, and then I have a kbt, which was there. I think with a minus, but then I have another minus from here, this cancel. And what I have there is I have a 2 sen h of h epsilon and q, h plus epsilon and q. And then there is a beta here. Kappa bt, 2 seno iperbolico, sì, and then I have this an additional beta here outside because I'm deriving with respect to h, this cancel. Okay. And therefore, finally, the magnetization per particle, this small m, is equal to the hyperbolic tangent of h plus m epsilon q. Okay. So let me write this on top so that we can we have it there and we can play with it. So in the mean field approximation, MF stands for mean field. We find that M is equal to the hyperbolic tangent of H plus M epsilon Q. Now you see that this equation here contains, and this is typical of mean field approximation that provides a nonlinear equation in the magnetization in this case, but in general is what is called the order parameter that we will define in a moment. And you see that this is a nonlinear equation for m. It must be solved, well, basically it must be solved numerically, okay? There's no analytical solution for that. But at least we can understand qualitatively what's going to happen when h is equal to 0. So let's take h equal to 0. And in this case, I have that m is equal to the hyperbolic tangent of m epsilon q. Now, let's try to do a plot of this quantity. I think I forgot something there. I think I forgot the beta. So please correct if you have, if you do not have the beta. Ce l'avete il beta? Mi sono dimenticato di scriverlo, there is a beta here. Okay. From the previous formula, that one was there. So there was a beta. Okay, so there is a beta here. So for h equal to 0, I have the hyperbolic tangent of beta m epsilon q equal to m. Okay? So now let's try to do a plot of this quantity. Let's call it f1 and this is f2 and see what happens, at least qualitatively when I want to find the numerical solution of this equation. Now, the first, so the left-hand side is just a straight line. This is one, f1. The second is a hyperbolic tangent that has the following behavior. Well, it depends on the temperature, of course. Now, suppose that we have a large temperature that I will call T2. T2. And I'm plotting F2. Here is F2 for T2. And now let me decrease the temperature. So when the temperature is large, 1 over beta is small, and therefore this guy is going to 0. So for beta infinity, for T infinity, beta is equal to 0, the hyperbolic tangent is 0. So then it will be it will be flat on the x-axis. Whereas in the opposite, when t is small, beta is large, and then my hyperbolic tangent actually starts to have a different behavior. Let me try to do a plot which is reasonable, so that we can reasonably understand what's going on. So something like that. Okay, so this is for P. 1, this is F1, and let's consider the case that T2 is larger than T1. Of course, now at infinity, what I'm plotting here is F1 and F2 as a function of m. At infinity, the hyperbolic tangent is going to 1, no? Which means that the magnetization is 1, so the magnetization per particle is 1. That means that basically my spins are aligned in the same direction. Okay. Okay, so let me comment the most important part, which is actually this. So you see that here there is always a point, a crossing point, which is m equals 0. So for m equals 0, this equation is satisfied. So it's a normal. So it's a good solution of my problem. It's a possibility in which the average magnetization per particle is 0, and this is basically the standard behavior in which you don't have any phase transition. It is the case, for instance, that we had at the beginning of the course when playing with spins, and we said that the magnetization is equal to the average magnetization is equal to 0, and so here is the same. But now the most important part, of course, is that when the temperature is small enough, I have two more intersections here and here. So what happens due to this nonlinear behavior of this equation, is that I have actually, depending on the temperature, I have three solutions. I could have three solutions in the sense for high temperature, which is the case of T2, I just have one solution, which is m equal to 0. For small temperature, and now we will see what does it mean small, we have actually three solutions. One which is m equal to 0 again, and then we have two more solutions which corresponds to a average magnetization different from 0. Okay, let's call it m bar. And these two solutions are m bar and minus m bar. They are specular with respect to the origin, which are different from 0. Okay. Now, of course, this is the basically the core of the magnetization, the ferromagnetic behavior. No? If you have large temperature, the average magnetization is 0. If you have small enough temperature, the average magnetization is different from 0. Consider here that we have H equal to 0. So we have a magnetization for small temperature, even in absence of H, we could have M different from 0. Okay, which of course is a different behavior with respect to the paramagnetic case, which is the case that we analyzed in the case of the one-dimensional Ising model was a situation of paramagnetism, in which if the external field is 0, also the magnetization is 0. Now, this is the case for large temperature, whereas for small temperature, I could have values of m different from 0. Actually, I have two values, one pointing in one direction, the other pointing in just the opposite direction. So here, remember that we have spin with the possibility of being up and down. The model can be generalized to the Heisenberg model. But so this is basically the issue, okay, the core of this business. Now let's be more quantitative and check which is the temperature for which I start to have these two more solutions. These two non-trivial solutions. And you see here that the reason, so the criterion is simple, and is basically when the tangent of f1 and f2 are equal, no? Now the tangent of f1 is 1, so if I do the derivative f1 prime is 1, and I impose that this is equal to the derivative of f2, computed, of course, n equal to 0. Okay, now f2 was an hyperbolic tangent, pratica divergente, vediamo dove stiamo qua. It was an hyperbolic tangent, and therefore when I do the derivative of this guy, what I get is that 1 is equal to cos h squared of beta m epsilon q. Then I have, I'm deriving with respect to m, so I have a beta and beta epsilon q, and this must be computed from m equals 0, because at m equals 0, you see that, maybe I do a plot again, but I think maybe you understand what I'm saying. But what I'm trying to find basically the condition at which so this is F1 and F2 is just this one. Okay, so there's a tangent at m equals 0 is equal to 1. And the condition is that, of course, the derivative of the left-hand side and the right-hand side are the same. Now, left-hand side is 1, the right-hand side has this quantity that computed at m equals 0 is beta epsilon q equal 1. Okay? So this condition is obtained when 1 is equal to beta epsilon q. That means that you have a critical temperature, beta, that defines actually the critical temperature for this phenomenon, which is kBT, or if you want Tc, is equal to epsilon q divided by kB. Okay? So this is the critical temperature. Forse cancello questo blocco qua. So this is called critical temperature. What happens is that for T larger than Tc, I just have one solution, which is m equal to 0. For T smaller than Tc, I have three solutions actually. M equal to 0, and m bar, and minus m bar. We will see in a moment that actually the solution at m equals 0, we can forget about it because it is not the one corresponding to the minimum of the free energy. So actually, what is important below Tc, what is physically realized, is really one of the two possible magnetization different from 0, which is m bar and minus m bar, because this will minimize the free energy actually, as we will see in a moment. Okay, so now this is the critical temperature, which is of course the point at which all these critical phenomena are occurring. So the behavior that we want to study of our system is the behavior close to the critical temperature. Okay, so some notes. One, if I put epsilon, sorry, if I put q equal to 2, so for one-dimensionalizing, I will get that q is equal of 2 because the number of closest spins is 2, and therefore I would predict midfield approximation of phase condition which, however, is not present in the correct analytical solution of 1D Ising. This we saw, we said it before. So you see that when doing the midfield approximation, I do not recover the result for the one-dimensionalizing model that was a correct result, it was analytical, because I would just need to put q equal to 2, so then I would predict a finite value of Tc, which is wrong, of course, and this is due to the fact that the midfield approximation is indeed an approximation, of course, it's an approximation. And actually one can show, we will not do it, But one can show is that the higher the dimension, the higher the dimensionality, the higher the number of dimensions, so 2, 3, 4, and so on and so forth, the better the approximation. Okay, so this is a general statement that I will not justify. Basically, what one can show, the way to do it is basically to compute the fluctuations or to estimate the fluctuations of the magnetization and compare them with the average magnetization and impose the average magnetization, so that impose the fluctuations are small, and one obtain a limit on the number of dimensions. And one sees that the larger the number of dimensions, the better the midfield approximation is. Okay. Now, in the case of one-dimensionalizing model, one can show really analytically that this midfield approximation is not correct. In the case of two-dimension, indeed, at least, so let me remove this, at least the qualitative behavior is correct in the sense that we find in midfield a critical temperature, and so a critical phenomena, and at a final value of Tc, but the real solution, so in one two-dimensionalizing model, actually one will find that in mean field, what we get from there is that Tc is equal to epsilon 4 divided by kb, where 4 is for a lattice a square lattice, and which remember that we have 4 closest spin, no? So if I am in this lattice and I'm sitting in this spin here, the closest are 1, 2, 3, and 4, okay, for a square lattice. So with this geometry, at least, okay? So then by using this formula, Q is equal to 4, and then I would predict in mean field that the critical temperature is 4 epsilon divided by Kb, whereas in the 2D, wherein in the analytical solution, this is the Onsager solution, one finds that actually Tc is equal to, let me quote the full result. One gets 2 epsilon divided by kb, and here there is a log of 1 plus square root of 2, which I think is close to 2.27 epsilon divided by kb. Okay. So you see that there is a difference. Here I have 4, and here we have 2.27. So this is, of course, the correct one because this is the full calculation. This is a mean-field approximation. Now, of course, with respect to the one-dimensionalizing, now it works better, and it will actually work better, even better, when the number of dimensions is larger. Okay, so now let's study, of course, more. Let's try to characterize a little bit more what's going on at the critical point. So let me write again this formula for M, which was the hyperbolic tangent of beta and epsilon q. our starting point. Now, what I want to do now is to study what happens close to TC. Okay. Now, qualitatively, we are already seeing that what's going on there, and we will characterize this. There appears a new solution, which is a solution in which m is different from 0 and it has a finite value. Now, this is an example, a paradigmatic example of spontaneous breaking of symmetry, because you go from a situation at high temperature in which basically there is no there's no magnetization, because on average the number of up and the number of down will be the same, and so on average there is no magnetization. Whereas for t smaller than Tc, now since we have here the possibility of just spin up and spin down, we don't have the full angle, but we just have two possibilities for the direction of the magnetization, which is up or down. And what's going on there is that basically the system decides at some point below Tc to spontaneously to have a spontaneous magnetization. And this is an example of spontaneous symmetry breaking, because I go from a situation in which basically there's no preferred direction, up and down, the same, into a situation in which, for instance, all the spins are up or all the spins are down. Okay, so this is a well, a paradigm for the spontaneous breaking of symmetry, because if you imagine the same system, but in a more complicated setup in which the spin actually can be oriented in a full angle, range of angle, then basically having a magnetization in a certain direction would break rotational symmetry. Okay. Now, of course, for those of you who have already done a course of quantum field theory or even particle physics, you might have seen already examples of spontaneous symmetry breaking, you know? Sì, avete già viste queste cose.
Il professor Pappalardo sta facendo adesso
X.
alcuni esempi
Okay.
campo di X, esatto.
Okay, yeah. So this kind of physics, so the spontaneous symmetry break, I will comment more on this. I will do the plot. It will be very clear when we do the plot of the free energy. It's basically comes from statistical mechanics. Okay, so it's a phenomenon of statistical mechanics that is related, if you want, to ferromagnetism, because this is a ferromagnetism problem that actually is more general. It's a general feature. Actually, the critical point, this critical temperature, we saw it before. It exists also in the case of a real gas computed within the van der Waals equation of state. Also, that in that case, we saw that there is a critical point, and actually, the behavior close to the critical point is just the same as this one. Okay, so this is somehow surprising. In one case, I have a gas or particle with a certain kind of interaction, excluded volume, and an attractive potential. Whereas here you have a totally different system with spins which are localized in discrete position. They are in a lattice, but nevertheless they show a behavior which is a critical behavior, which is actually will be the same at TC. Okay, so this is somehow very surprising. And okay, so let me start again from this formula for M. And what I do now is to make an expansion close to TC from the left-hand side, where I know that the magnetization is different from 0. Okay, so first of all, let's write this as, so M is equal to hyperbolic tangent of now this n, and epsilon q divided by kb is just Tc for what is written, what was written before. So this is actually n divided times Tc divided by T, and it's beta. Okay. Now let me expand to make a series close to Tc, and actually when I do T approaching Tc from the left, from below, where I know that there is there will be a finite value of the magnetization. Okay, for T larger than Tc, or if you want for T approaching Tc from above, we know that M is identically vanishing. Okay, whereas in the case of T approaching Tc from below, we have that the magnetization is zero, but the limit is not zero, in the sense that we will see that actually there is a divergence of the derivative. Okay, so now we'll do the calculation. So what we do is to expand. M is anyway very small. Okay, so for T approaching Tc from below, in any case, M is approaching zero. And then I can use the expansion of the hyperbolic tangent that I'm sure that everyone remember. This is the following: is x cubed divided by 3. And so I can write here, well, basically this quantity here. So it's m Tc divided by T minus 1/3, and then the same quantity. So m cubed Tc divided by T cubed. Ok? Allora facciamo, intendiamo qua. So now let me collect n here. So n, so then I have about 1 minus Tc divided by T, and then I have a plus 1/3 m squared Tc divided by T to the power of 3, and then this is equal to 0. 1 meno Tc diviso T, 1/3 m quadro, ok. Now this is equal to 0, and therefore I get as possible solution n0. It's a possible solution. And then I have two more solutions which are provided by the same by the following formula. So n is equal to plus minus. So here I put this on the left hand side, and so this Tc minus T divided by T. Okay, let me write the result directly. Si può fare ovviamente. Tc minus T divided by T, and then there is 3T divided by Tc cubed. Okay. So of course now I have a trivial solution that is m equal to 0, and since we are approaching the Tc from below, we have two more solutions close to m equal to 0, so we are close to the critical point, which are provided by this formula. Okay. Now it's very common to write this quantity in terms of sort of reduced temperature, which will characterize all the behavior of the critical point, which is this quantity T, which is the difference between Tc divided by Tc. So basically, this quantity T is a deviation from the critical point. If T is equal to 0, or is approaching 0 from left and from the right, I'm approaching basically the critical point. So when introducing this quantity, T, I can rewrite the magnetization M as follows. Plus minus. Here I have a minus 3 T, that comes from this quantity. And then I can rewrite the T divided by Tc cubed as T plus 1 to the power of 3. Okay? Now, what is important in general when dealing with critical phenomena is the behavior of M, of the scaling, better to say, the scaling of M close to T equals 0, which is the scaling of M, the magnetization, close to the critical point, which in this case is provided by the following formula. The scaling of M is plus minus. Let me put 60. Here is negative, and here I have a minus. Let me put absolute value. And so this will be the absolute value of T to the power of 1 half. Okay. And let's make a plot. So the plot that we can do is the following. Here I put M, and here I will put the temperature. So what happens is that I have at some point a critical temperature, Tc, which is provided by epsilon Q divided by Kb, and above this temperature, M is equal identically to 0, whereas below the critical temperature I found these two non-trivial solutions, and in particular close to the critical point we have used this expansion, and you see that we have a behavior which has a square root. M behaves as a square root of T. Which means that here I have an infinite derivative. So I have something like this. Okay, so if I derive, let me cancel this TC. If I derive M with respect to temperature or with respect to T, which is the same, I have a divergence of the derivative there, so therefore the behavior is like that, okay? The square root. This is T scaling as, M scaling as the P to the power of 1 half. And of course, when I go to even smaller temperature, at some point I will have the finite value, which will be plus 1 and minus 1. That to have let's say the proper solution, I should solve numerically the equation that we wrote before for M. So, but we are more interested now at the moment of what happens close to the critical point, which is exactly what I'm saying here. Now, notice an important thing is that so above Tc we have M equal to 0. Something weird is going on here at Tc, where the derivative is infinity, and below Tc, or at the same temperature, for a fixed value of the temperature, if you want, I have two solutions which are completely disconnected. They are completely separated. I could have this one, or I could have this one. They are both have the same, let's say, the same chance to appear. Okay. So this basically is the same feature, at least qualitatively, of what happens when I do the plot of a liquid gas phase transition, in which we usually make the plot P versus T. And here at some point for the liquid gas, here I have a liquid and here I have a gas. And we say that there is a line of first order phase transition which is ending in a critical point, which is this Tc in the critical value of the pressure. Okay. So now what happens in the liquid gas is that if I move along this line, I go from a situation in which the gas and the liquid are the same, that here would correspond to magnetization equal to 0. Then at the critical point, I have something which is now called the order parameter, which is in this case m, and in this case actually the density, one of the two phases. They start to make something crazy, and actually below this value of Tc, I have the separation of the two phases. So here at the critical point, liquid and gas are the same, I cannot distinguish them, and below I can distinguish them because they separate into different phases characterized by two different densities. The liquid has a larger density with respect to the gas. Here, the situation, at least qualitatively, is similar, but actually also for what concerns the behavior of several quantities that we are going to mention in a moment. But here, what is separating, if you want, is not a liquid gas, but it's the fact that I could have magnetization plus one, or say the direction with a, let's say, net number of magnets of spin in the direction up, or just the opposite. Okay, so here magnetization 0, and then I have a breaking of symmetry that provides a preferred direction. Here I have 0 difference between the density of liquid and gas, and then at some point I have a jump in density from the liquid to the gas. Okay? Questo è quello lì. Vabbè, questo ve l'ho detto. So notice also that now we are going to characterize a little bit better this quantity, but notice that we here we have this behavior of m at the square root of t, and then of course we will have a divergence of m with respect to the derivative of m with respect to t at the critical point. Okay. Now let me make a plot just to show what's going on in the case in which h is different from 0, so if the external field is different from 0, so now I remind you that here we are studying the case in which the external magnetic field is 0. Nevertheless, we find a net magnetization, okay? Now let's put a magnetic field different from 0, and if I do the same plot in which here I have magnetization and here I have T, then in the case in which h is equal to 0, we get this behavior that we said before. So this is for h equal to 0. If h is different from 0, when computing the solution of this numerical equation, one finds something like that. For h larger than 0, one finds a smooth behavior like this. That corresponds to the fact that regardless of the temperature, I have that the magnetization of my system is finite and is following the magnetic field. It's a paramagnetic, it's the case of paramagnetism. Okay, and let me put this h equals 0 here. If the magnetic field is negative, this M, it goes the other direction, okay? So I have in any case a smooth behavior. So smooth behavior of M when H is different from 0. So in this case, I do not have phase transition. Okay. And actually, just to stress a little more the comparison between the liquid-gas phase transition and the critical point and this kind of phase transition, let me plot the magnetization now as a function of H, which is a different plot with respect to this one, because here I'm plotting M as a function of T for different values of H, whereas here I'm plotting M as a function of H for different values of T. Now, if T is larger than Tc, I will get something like this. T larger than Tc, which is the behavior of a paramagnetic system. Okay? Paramagnetic. So the system has a magnetization per particle, average magnetization per particle, which follows basically the external magnetic field for T larger than Tc. And for T equal to Tc, let's try to make the plot in a reasonable way. So here I will have a behavior like this one. No, lo faccio sotto le domande. Cerchiamo di farlo meglio. Adesso disegnare malissimo. So, should be something like this, in which at this point the derivative is infinity. So T equal to Tc. And finally, when T is larger than Tc, so sorry, smaller than Tc, I have this, here we need some shocks to the color. I will have a behavior like this. Okay, so this corresponds to T smaller than Tc. Now you see that here I have a sort of jump of the magnetization when I change the magnetic field. Okay, so for T less than Tc. If the magnetic field is positive, then the magnetization follows the magnetic field. But if I switch it off, I still have a finite value of the magnetization, okay, which is still positive, but it's finite and it's positive. If I go from the other side, for a negative magnetic field, again the magnetization has the same sign of the magnetic field and decreases when I decrease the strength of the magnetic field. But if I switch it off, then at some point I will reach, in any case, a finite value of the magnetization. And here I have a jump, okay? I have a jump of the magnetization as a function of H. Now, of course, there are many things that one can say about this plot. If I do continue this, I will have what is called hysteresis. Avete visto l'hysteresis da qualche parte, forse, vero? Which is somehow the metastable branch of this equation of this plot, in the sense that actually, if I increase H, I will have a behavior like this, so that the magnetization will still be il ciclo di stereo funziona così, no? Vabbè, adesso si disegnò malissimo, però una cosa del genere. So that the fact that, but I don't want to discuss it, but I have basically what is called physical, like a metastable magnetization of my system, which correspond to these statistics. Okay, but okay, we will not discuss because this is non-equilibrium phenomenon that I'm not going to discuss now. In any case, what is interesting to us for what we are discussing now is that we have this behavior below TC. By the way, TC you can call it if you want critical temperature or QV temperature because it's the temperature under which no, it is smaller than TC. You have a ferromagnets, ferromagnets. Okay, so if you want, this is the QV temperature. But this jump, what reminds us? Well, it reminds us another jump that we saw now in the case of the liquid gas phase transition. Because when I do the plot of not P versus T, which is the phase diagram, but if I do the plot of P versus volume, now remember that it was like that. So here is the isotherm for T equal to Tc, and below Tc I have, sorry, let's do it in a better way. I have this jump in which the pressure is constant, and I have a jump in volume which corresponds to the jump in the density of the liquid and the gas. Okay, the specific volumes of the two phases are different. So this jump here would correspond to this jump here of demagnetization. Okay, and this is the behavior of the so the line of coexistence of the two of the liquid and the gas, which ends at the critical point, which is this point here. Okay, so the physics that is in here in the real gas, the van der Waals equation of state, show some very striking similarities with the physics of the Ising model, or if you want, of the ferromagnets and paramagnets. Okay, they're the same kind of phenomenon. That's why people are talking about universality, because we can have very different systems, but behaving qualitatively close to the critical point in a very similar way. Okay, so now let's start to study higher order derivatives, if you want, of the free energy, in order to characterize a little bit more what happens at the critical point. And let us introduce numbers that are called critical exponents, that characterize indeed the second order phase transition like this one. So, second quantity that we want to define, I think we saw it already in the case of the lambda magnetism, is the isothermal susceptibility, which we call the chi of t, which is a function of t and h, and it is provided by the derivative of m with respect to h at a fixed temperature. This isothermal susceptibility. Isothermal susceptibility. Okay. Now to compute this quantity, we start again from our solution for m, which was that m was equal to the hyperbolic tangent of beta, and here I have h plus m epsilon q. Now I do the derivative with respect to h of this quantity on the left and on the right by fixing the temperature. And here on the left, I get the isothermal, of course, susceptibility by definition. So derive with respect to h, and here we'll have just chi of t, and here instead I will have il coseno iperbolico of so beta h plus m epsilon q. And then at the numerator we will have a beta which multiplies 1, that is the derivative of this quantity with respect to itself, plus epsilon q, and here we have the derivative of m with respect to h, okay, at fixed temperature, which is just chi of t again, okay. Therefore, I can, from here, I can find this chi of t, which is here and here, and just with the math, the algebra, and I get the following result. So we will get the chi of t in general is provided by this expression, which is beta divided by the cos h squared of this quantity here. So beta h plus m epsilon q. Then there is a beta at the denominator, there is a beta epsilon q that comes from this guy here, minus beta epsilon q. And I think that's it. Vediamo se ho scritto tutto. Beta, coseno iperbolico al quadrato, h più m meno beta epsilon. Okay, so now let's compute h in order to define this quantity, this critical exponent. Let's compute chi of t for h equal to 0. Allora, cambio gesso. And yeah, so what we get is beta divided by the cos h squared of h is equal to 0. And here I have beta m epsilon q, which can be written as beta times Tc divided by T. And m Tc divided by T. And similarly here, this beta epsilon q is again Tc divided by T. Okay. Now, what I'm going to do is a rather trivial expansion of this quantity of this chi of t close to the critical point. So here we are at h equals 0, so we have fixed the magnetic field. So we have actually exploited the magnetic field to find a susceptibility, so to find the way m changes as a function of the magnetic field. And now we sit at h equal to 0. And what we'll do now to expand, or if you want to study the behavior of chi of t close to Tc, which means in the limit in which t is approaching, the small t is approaching Tc 0, sorry, 1 and 2, t approaching 0 from above, and t approaching 0 from below, where I remind you that t was equal to t minus Tc divided by Tc, is the deviation from the critical temperature. Okay. Now, okay, so this again, let's say it's basically just math. So we'll just sketch the calculation. So the formula that we need is the following, is this one. Now, if t is approaching 0 from above, which means that t is larger than tc, I know that m is equal to 0, is identically equal to 0, and therefore the chi of t is just beta divided by this. Now this is 1 minus tc divided by t. Okay, which can be written in a slightly different way. So basically now this is 1 divided by kb t. Okay, so let me put the kb outside, and here I have a t here minus tc. And let me multiply this quantity by tc, and tc, and this is now equal to 1 divided by kb tc and t. Okay, 1 divided by kb tc t. For reasons that will be clear in a moment, let me write this as kb tc times the modulus of t, even if t is larger than 0. It's just a useful way, because below I will write again the same quantity below tc, and therefore there I will use the modulus of t. Now this provides a scaling of as you see. As you see already from here, the susceptibility diverges at t equals 0 from above, no? So note that close to Tc, actually we have t approaching Tc from above, we have a divergence of the susceptibility, okay? So chi of t diverges. Diverges as 1 over t, okay? And this corresponds to the fact that when I was plotting a t equal to tc dm as a function of h, I was plotting the curve having an infinite derivative at t equal to tc correspond at h equal to 0. Okay. Now let's study the same behavior now in the case in which t is approaching 0 from below. Now in this case the situation is a little bit more tricky, in the sense that my chi t, dunque com'è che lo facciamo? Questo qua, facciamo direttamente il coseno. Ok, this chi t, okay, let me write first the formula that we had before. So this chi t, it was beta divided by cos square hyperbolic of m tc divided by t minus tc divided by t. Now let me use, now we are 0 from below, where m is of course approaching 0, but it is not identically 0 as in the case of above. So I will have to include, let's say, some more terms in the expansion, okay? And so let's expand, also let's use this expansion of the cosinus. So if I have the cos of hx is close to 1 plus x squared divided by 2 plus blah blah. So m, even from below, is approaching 0, so then I can use an expansion, and I will stop at the second order, okay? Above, I do not have to use an expansion because it's identically 0. Okay, whereas here it's approaching 0, but actually it has an infinite slope. Okay, so let's use this in here. So the chi of t would be something like beta, and now here we use this fact. So the first term, of course, is 1. Then I have mtc divided by t squared, and 1/2. So I have a 1/2 and tc divided by t squared, and then there is a squared because this was a cos squared, okay, minus tc divided by t. Okay, so now the calculation is just a little bit of algebra, but let us remember that when approaching t equals 0, m was behaving as the square root of t, and therefore, well, actually, there was also 1 plus t here, and then there was 3, and then there was this constant here. Okay? Just to be more precise, let me make so this was 1 plus t to the power of 3, and then we have 3, and then the modulus of t. Okay, this was the behavior of the magnetization below Tc. Now, of course, this is equal or almost equal to 3t square root, because we are close to t equals 0, so then I can neglect this term, just a correction. Okay. Now what we do is to use this in here. Okay. So instead of m, we will write this square root of 3 modulus of Tc. Okay, so now there's a little bit of algebra. I think it's not so useful that I do this algebra. And what you get at the end is that the chi of t, when t is approaching 0 from below, behaves like 1 divided by 2 kb Tc, and then t. Okay. Now, the fact that you get t here, as before, comes from the fact that you have a square here, and you have another square, and you have sorry. Let me see, where does it come from? Sì, vabbè, perché c'è un quadrato, c'è una radice. Okay. And maybe if you want at the end, I can do the calculation, but it's just really putting, instead of m, we put it here 3 square root of 3 modulus of t, and one gets the behavior that I showed before. Okay, so now chi of t gain close to the critical point now from below behaves exactly in the same way, but for this factor of 2. Okay, but the singularity is the same. So now to make to summarize, let's put it here. Summarize this kind of t is a function of t, and we said h equal to 0, is behaving in the following way. For t approaching 0 from above, we have a 1 divided by kb tc modulus of t, whereas from t approaching 0 from below, it's just the same apart from a factor of 2. Now, to be, for people studying really critical phenomena, for a course oriented in critical phenomena, one can show that this factor of 2 and this factor of 1 here are actually universal also then, but we will not discuss this feature. The important thing that we need to stress is that we have a singularity of chi close to Tc. So if I make a plot of T, and here I have Tc, I have a divergence of chi of T. Okay. Good. Now we will introduce in a moment, just a moment. Non so se ce la faccio finire oggi. Vabbè. This scaling of magnetization and susceptibility close to the critical point, and these exponents are called critical exponents. So in this case, the critical exponent is 1 or -1. Okay, but I will introduce them in a moment. Okay. Now, let me comment a little bit more on the interpretation, which is actually really remarkable, of what's going on when I have this critical temperature, by looking at what happens to the free energy. This is very important because the plot that I'm going to show you is basically the core of spontaneous symmetry breaking that we are using also for studying the Higgs boson. Okay. Now, so let's study the free energy of A close to Tc. So for the moment we have seen the behavior of M, and M scales as the square root of T. We have studied the behavior of the susceptibility, which has a divergence in T equals 0. Now we are going to study the behavior of A, and as you will see, this provides really very intuitive insight on what's going on with the phase transition. Okay, so let's start from the formula, and let's put it H equal to 0 for the moment. Then we will put also H different from 0. And A divided by N was provided by this formula, was an epsilon q m squared divided by 2, epsilon q m squared divided by 2. Then I have a minus kbt and a log, which I can split into a kbt log of 2, because I had twice the hyperbolic cosine, minus kbt, minus kbt log of cos, hyperbolic cos, sorry, of beta m epsilon q. So this is the formula for mean field, of course, for the free energy per particle. Okay. Now, close to the critical point, close to Tc, we know that m is approaching 0, okay, from above and from below. But actually from above is identically 0, so it's not so interesting. But come si dice? Well, what is mostly interesting, of course, is the behavior below, where m has a different, so it's approaching 0, but it's not identically vanishing. Okay, so let us use the fact that I can expand this function in the following way. So this is equal for x small to x squared divided by 2 minus x to the power of 4 divided by 12 plus blah blah. So what I'm going to do now is to expand, to make a series of this quantity log of cosine, hyperbolic cosine, as a function close to n equal to 0, okay, by using this. Okay. So a divided by n is minus k dt log of 2, which is not very important actually, it's just a shift. When I will do a plot of a divided by n as a function of n, it's just a shift, so it's not very important. And then I have epsilon q m squared divided by 2, which is this quantity here. And then I have a minus k dt, which is this, and x squared divided by 2. So here I have a 2, and then I have an x squared, which is beta squared m squared epsilon squared squared. So we have a beta and epsilon q squared. And finally, here I have a minus, and the minus there becomes a plus, k dt divided by 12. And I have beta and epsilon to the power of 4. Beta and epsilon to the power of 4. Okay, so this is the expansion of free energy per particle close to the critical point, so when m is approaching 0. Okay, from below, because from above it will be m will be negative. So you see now that this has a very interesting behavior in the sense that there's a constant term, constant with respect to n, so it's just a shift. Then there is a quadratic term, m squared, and then there is a quartic term. Okay? Actually, I can reshuffle a little bit this quantity by introducing the critical temperature, which is just epsilon q divided by kb, and reshuffling a little bit this formula, and I can arrive at the following expression for A. So, so this is equal to minus k dt, the log of 2, this term here. Then I can collect here epsilon q m squared divided by 2. And let me also collect, vediamo un po', epsilon q m squared divided by 2. Let me also collect t here. And here I will have 1 minus tc. Sorry, no. This t minus tc. Vediamo da dove viene questa roba. Okay, so of course, if I put this here, I have this term here, and then the second comes from the fact that I have TC divided by T comes from the fact that I have a beta squared here, and I have a KBT here. So if this actually will be KBT, then I have a beta squared, which is KBT squared. On KBT beta squared, then I have a m squared and epsilon q, which is actually KBTC. Okay, so that's why I get at the end we have this TC there. Okay, a ratio between TC and T, and the m squared is collected. Ok? Quindi c'ho il meno kbt log 2, epsilon q m squared 2t, t minus tc, ok? Plus 1 divided by 12, kb, 3b, m to the power of 4, it comes from here. And here I can also again introduce, so I have a beta to the power of 4, kbt, and then epsilon q is just epsilon q is tc divided by kb. Okay, and so if you introduce tc here, you will get 112 kb m squared, and here there is a t c to the power of 4 divided by t to the power of 3. Okay. Vediamo se è tutto giusto. K epsilon Q, va bene. Un dodicesimo, quell'affare lì. Uguale. Now this is the same kbt log 2 plus, let me introduce a constant a here, which multiplies t minus tc and n squared. Where a is epsilon q divided by 2 t. Okay, what is left there? Epsilon q divided by 2t, and then I have m squared a. Okay. Of course, this a is a positive quantity. The fact that it is positive is important. You will see in a moment why. Then I have plus another quantity that we call b, and m to the power of 4, where b is equal to what is left there, so it's a kb divided by 12, and I have a tc to the power of 4 and t to the power of 3, which is again a positive quantity. Okay. So now these are aquatic, no? So these are a divided by n, and this is a function of n and t, if you want. It depends on the magnetization n, and depends on the temperature. Okay. Now we can try to do a plot of this quantity of the free energy as a function of m and for different values of Tc. Sorry, for different values of t. Now, if t is larger than Tc, apart from this shift that is not important, here I have aquatic with two positive numbers here. So this is positive and this is positive, and therefore the plot of n divided by a divided by n as a function of m will be something like this. So it's 0 at m equals 0, and BA is like aquatic. Okay? This is just because this is positive. Okay. Now, what happens when t is equal, so this is for t larger than tc. What happens when t is equal to tc? Now is again something like this. But now this term disappears, and apart from this shift, this is just m to the power of 4. So therefore, I will have, let's say, 1, 2, and 3 derivatives which are 0 here, right? Okay, so therefore it's flatter here. Okay, whereas before the leading term, so I have two derivatives. Two derivatives vanishing there, well, I have to do the calculation. But okay, in any case, here, un attimo, no, la prima derivata sembra. Here is flatter here, because it's aquatic, without this term here, okay? Okay, but qualitatively the behavior is the same. And now, and this is the magic of phase transition, critical phenomenon, is that when I do the plot for t smaller than tc, it's completely different. Because now, this term here, okay, let me write again what was the form. This is a minus k t log of 2 plus a t minus tc m to the power of 2 plus b m squared. Now, if t is smaller than tc, then you see that this is negative, and the behavior is completely different now. And it's actually provided by something like this, which is the in 3 dimension would be the famous Mexican hat. Okay, so this is for t smaller than tc. Well, you see that in here, m equals 0 is corresponds to a maximum of a divided by n. Therefore, the system here is actually unstable. The system, once you are below Tc, would like to go either here or here. And so these are two finite values of the magnetization. Let's call it m star and this minus m star. And so the system will roll or will set at the minimum of a divided by n, which occurs at a finite value m star or minus m, sorry, m bar or minus m bar. Okay, so either here or here. So this picture is basically the explanation of this critical phenomenon. Spontaneous symmetry breaking is here in the sense that below the C, your system will sit in one of these two minima. Okay, these are degenerate in the sense that they are both, let's say, the same probability to be occupied. Okay, now if you do the calculation in 3 dimensions, you will have a rotational invariance of this minima, and actually it will become the famous Mexican hat that you might have seen in the case of il potenziale di X. Ok, let me see cosa vi devo dire adesso di questo. Okay, so This plot basically explains why I have a magnetization at T below Tc, because my free energy, which is the quantity that must be minimized to obey the second principle of thermodynamics, as a minimum at a finite value of n. Okay? Now let's sketch a bit what happens when h is actually different from 0. And when h is different from 0, what is the difference? So at some point in the expression of a divided by n, I have some terms, and at some point I have the minus, well, actually it was a minus kbt log of the cross h of beta and beta h plus n epsilon q. Okay. Now, since I was doing an expansion series around m equals 0, in presence of h different from 0, I will have also a linear term in m. Okay, so for m equals 0, of course I will have a constant, so this function computed in m equals 0. Then I will have a term which is now linear in m, because the first derivative of this quantity now is different from 0. The first derivative with respect to m. So when I have the series, I have some numbers, and then I have the numbers which are proportional to m squared and 4, blah blah. But I have also a linear term in m. Where does this linear term come from? From the derivative of this quantity with respect to m computed at n equals 0, which is finite for the case in which h is different from 0. And this linear term will actually be something like the cos h of beta h plus n epsilon q. And here you have sine hyperbolic of beta h plus n epsilon q. And then I think I have epsilon q beta, epsilon q beta, with a minus, and this must be computed for n equals to 0 and multiplied by n. Okay, so the linear term will be something, of course, which is proportional to n, and this is the derivative with respect to n computed for n equals 0. Okay. Now let me introduce this quantity. Okay, so this is minus. Let me put m equal to 0, so it's a epsilon q beta. And then I have the tangent, the hyperbolic tangent of beta h, okay, times n. And you see here that this coefficient is positive or negative depending on the value of h. So if I call it C, these terms, okay, C is positive for H positive, because
it has the parity of the hyperbolic tangent, whereas C is negative for H negative. Okay? So therefore, in the formula, in this expansion of the free energy around the critical point, in presence of a magnetic field, I will have this additional linear term, okay? So H divided by N. So it has terms as before, but it has also a minus plus Cn, which is the linear term, where C, as I said before, is larger than this positive if H is positive, and C is negative if H is negative. Okay. Now it's a matter of doing the plot, basically. Now this is again a quartic, but there is a linear term in M that changes a little bit the structure of this plot, and actually it spoils the critical behavior in terms of phase transition. So if you do the plot, as I said also before, so suppose that we want to do the plot for H larger than 0, if T is larger than Tc and you do the plot, you will get something like this. With a finite value of magnetization, which is different from 0. Okay? The minimum of the free energy occurs this time at the finite value of m, and this finite value of m is driven by the values of the magnetic field. Okay? The larger the magnetic field, the larger the value of m. If I change the strength of the magnetic field, I can move this m not to higher or smaller values. This is the behavior at T larger than Tc, whereas the behavior at T smaller than Tc is actually, it has a more complicated structure, would be something like this, but still it has a finite value and different from 0, which however basically changes continuously, so at a fixed value of H by changing the temperature and changes continuously. Okay, so let me write the sentence. So at fixed H by changing T and changes continuously. So no phase transition in this case. Okay, and this we have mentioned also before. Okay. Now let me put some definition in here. So this M is an example that will be generalized in the Landau-Ginzburg theory. What is called an order parameter. The order parameter characterizes the second order phase transition and typically it is a scalar or it could be also a vector depending, typically this quantity, this order parameter, has zero expectation value at large temperature. So symmetry not broken. So if you want symmetry still present, whereas it gets a finite expectation value at T smaller than a certain critical temperature, for which the symmetry is spontaneously broken. Okay. Now, in the case of the Ising model, the magnetization is provided. So the order parameter and the name order parameters basically is just the meaning of having the fact that when you are at large temperature, the orientation is just random. Okay. Whereas if you are at small temperature, there's some order in the system in the sense that spins would like to point in the same direction. Okay, that's why it's called order parameter. And in the case of the Ising model, this order parameter that characterize, if you want, the height, so that differentiate between the high temperature behavior, the behavior at small Tc, is the magnetization. In the case, for instance, of a liquid gas phase transition, a possibility for the order parameter is instead, for instance, the density jump of the two phases of the liquid gas phase transition. Okay, this density jump is zero when you are above Tc, whereas it's finite when you are below Tc. Now, this quantity appears somewhere in in all the other phase transitions. These are the two that we mentioned here, so Ising model and liquid gas, but one can play also with phase transition superfluid, well, in which we already said something in the sense that there is a kind of Bose-Einstein condensation phase transition, or in superconductivity, or in other possible setup. Okay. Now, in the last half hour, well, actually, maybe I will not. It is not too long, but let me mention what are these critical exponents that we will play with next time also. What are these critical exponents? The critical exponents basically are the exponents really that we see in the different quantities close to the critical point. Okay, so a first one is the following. M, we say that scales so close to C. We have a scaling of M as modulus of T to the power of beta, where in mean field approximation or Ising model, beta was 1/2. Okay. Now one can show fact that this is called beta is a tradition, basically. There's no reason, honestly, that I can find to call it beta. It's a standard notation that I will not change because it's the standard notation in the book. So this one example of critical exponent is beta, which characterizes the order parameter. So beta is the critical exponent associated with the order parameter. And we have computed that this is 1/2. And well, here I remind you that it was the deviation from TC. Then we have also derived the isothermal susceptibility at H equals 0. That had a scaling that goes like the modulus of T minus gamma, where gamma is equal to 1, again the Ising field. Again, the reason for which it's called gamma, there's no reason, and it's just a choice, and put a minus there. Okay? And this critical exponent gamma is associated with the susceptibility with this guy. And okay, so these are the only ones that we have computed up to now, but we are going to compute the other two critical exponents just in a moment. Okay, but let me make a comparison. So in mean field Ising, what we did now, beta is equal to 1/2 and gamma is equal to 1. Just to make a comparison, in the case of two-dimensional Ising exact, one instead find that beta is equal to 1 divided by 8, gamma is equal to 7 divided by 4, whereas in 3D Ising, for which the solution is numerical, and maybe some of you have done this in the course of the job, maybe, I don't know. I think you mentioned there strategy to compute critical exponents, no? Per quelli che hanno seguito quel corso, adesso non tutti chiaramente perché non è obbligatorio. Qualcuno
No.
sì, quelli che l'hanno seguito, no? Non si fa questa cosa? Vabbè, non insisto. Comunque, so in 3D Ising numerical, beta is equal to 0.31 and the gamma is 1.25, that are actually closer to the results in mean field, is 1/2 and this 1. And the reason is that the reason that I mentioned before, that it's a sentence that I will not prove, and the fact that a mean field gets better in higher dimension. Okay. Okay, so these are two examples of critical exponents, and there are other examples. These are the two that we mentioned today. One is associated with the heat capacity, and the other one which is associated with the equation of state. Okay? So behavior of CV close to TC. For CV, one introduce a scaling of CV as a function of T to the power of minus alpha, where alpha is the critical exponent associated with the heat capacity. And to compute it, we just need to remember that CV is the derivative of the internal energy with respect to T at constant volume, and can be also derived as a minus T squared, the second derivative of A, the free energy with respect to temperature at fixed volume. Okay. Now, in the case of the icing, actually the volume is not important because we have fixed speed, so the volume is not a variable that can change. Let me see what I need to say. Now, we will see in a moment that alpha is equal to 0 in mean-field icing, and it actually is different, but for some reason I do not have reported the value in 3D icing, is different from 0. And in two-dimensional icing, alpha is 0, but actually CV has a logarithmic divergence. Okay. Now the computation can be done basically just using the formula for the free energy. Let me just sketch the way to compute this heat capacity. And since we are studying the system close to TC, let's write directly the expression of A divided by N when using the expansion close to N equals 0, which was the following: kBT of 2 plus epsilon Q N squared divided by 2T. Here I have T minus 2C. And then I have plus KB divided by 12, TC divided by T cubed, and 4. Bene, HBT, epsilon Q, quello là, va bene. Dunque, HB diviso 12, 8. Okay, so now you can do the calculation of this quantity. By doing these two derivatives, which it's a matter of calculation, so it's not so important. And if I've done the calculation correct, one should get the following result. So epsilon Q M squared TC divided by T. Now, of course, since we are doing the second derivatives, this term drops, and we will just have contribution from these and these. Vediamo un po', quindi uno è quello, epsilon qm squared tc minus kb tc to the power of 4 m to the power of 4 and not t cubed. Now, if you do a plot of cb as a function of t, and here I have tc, for t larger than tc, this is vanishing, okay? Whereas it has a jump at t equal to c. So the behavior is like something like that. So that's why there is no divergence of CD at the critical point. Now, for t larger than tc, it's equal to 0 because this quantity here will depend just on this term here. So then the heat capacity is 0. And because n is equal to 0, no? So remember that here n is equal to 0. No? Whereas below, I get this expression here, and if you do the calculation, you get a final value of CD. Okay, it should be something like this. So there is no divergence but there is a jump. A jump. At least in mean field, okay? Whereas, as I said before, in the two-dimensionalizing, there is a logarithmic divergence, whereas for three-dimensionalizing, I have a divergence, actually. So alpha is different from zero. Now, the last critical exponent, so this alpha is equal to 0, the last critical exponent is the one associated with the equation of state. So let me introduce also one. Well, actually, there are other two of them, but we will introduce them next time. There are 6 in total, which are actually not independent, but I'm not sure I will have time to show this. Another critical exponent is the one associated with it's called the equation of state for a reason that will be clear in a moment. And basically, the other critical exponent is the scaling of M, the magnetization, as a function of H. And here, for reasons which are now really tradition, one introduces critical exponent, which is delta, and one writes M at t equals 0, and for H approaching 0. So the other critical exponent, which is delta, associated with the equation of state, is provided by the scaling of M with H, for H approaching 0 and T identically 0. Okay, this is the way it is defined. Now, in the case of the Ising model, we can compute this quantity trivially because we say that A divided by N it has a term that was a KBT log of 2, if I remember correctly, we wrote many times. Should be a KBT divided by 2 minus KBT, minus KBT log 2, sorry. Minus KBT is not important actually. Then I have A T minus TC M squared plus B M to the power of 4. And then I have minus plus C M, which is the linear term coming from the fact that I have a finite magnetic value of the magnetic field. And there is an H there. Vediamo un attimino. The H comes from the fact that aspettate un attimino, See, because I'm computing the derivative of this with respect to m, I should have an H there. So if you want, I mean, the better way to understand this term is that there is if you have an external magnetic field, there is a coupling, direct coupling between M and H, which is the standard one. So if the magnetic field is pointing in a certain direction, plus, you minimize the energy by having the M parallel to the magnetic field, or you maximize the energy if you have M opposite to the magnetic field. It's basically the point. Now, in this situation, this term is equal to 0 because we are sitting at t equals 0. And let me see. Now, what we have to do is to minimize this quantity with respect to m to find the magnetization. So m is found by minimizing a divided by n. So therefore, I will put the derivative of am with respect to m equals to 0. And when I do that, I get a quartic term, which becomes a cubic actually. So this equation will say that for b m to the power of 3 minus plus ch is equal to 0, from which I get that m scales as h to 1/3. Okay, apart from this plus minus is not important. The important thing is the scaling. And the scaling is that m scales as 1/3 h, from which we get the critical exponent delta associated with the equation of state. Delta is equal to 3 midfield Ising. Okay. Whereas, again, just to mention the result in two-dimensionalizing, and delta is 15 in this case, whereas in Ising 3-dimension, this is delta is equal to 5. Okay. Now, why is called the equation of state? I think that the reason is basically the comparison between what happens here with the magnetization and the magnetic field at the critical point, and what was the behavior of the pressure versus volume in a van der Waals gas, in which here, so this is T equal to Tc, we saw that the scaling of P in terms of volume was that P was scaling as volume to the power of 3, okay, close to Tc. This one, okay, so this point. So therefore, B, if you want to scale as 1/3 T to the 1/3, okay. And actually notice that, so actually we use this fact that here is a cubic also to solve the equation and to find the critical temperature, if I remember correctly, I've done it in this way, okay? And so you notice that, again, in a Ising model, I get this 1/3, and here you get the same behavior in a liquid gas phase transition, where here M and H correspond to volume and pressure. So if you want what is the external field here, in the liquid gas corresponds to the pressure, whereas the volume corresponds to M. This is correct because we said before that the way to characterize the phase transition is to find the finite value of M in the case of the Ising model, whereas in the liquid gas is the volume, or better, is the difference in volume of the two phases that characterize the phase transition. And also, you might remember that we said before when drawing the isotherms, there was a jump of the magnetization at fixed values of H, which was the ferromagnet basically, and similarly we have a jump of the volume, the isotherms at fixed pressure, okay, below Tc. So the behaviors are very similar, actually they are the same. So if one computes, let me write the sentence here. So these critical exponents, alpha, beta, gamma, delta, are the same in mean-field Ising and van der Waals liquid gas. Okay? Although the two systems are completely different. I mean, the reason for which at the end the behavior is similar, or one can classify several systems in what are called class of universality, is will be more clear probably next time when we introduce a thing which is called correlation function. That will somehow characterize the fact that when you are sitting at the critical point, you have long-range correlations. That means that if, let's say, at large temperature, or let's say far from the critical point, a single spin basically is talking with spins close by. When you are at the critical point, actually, you have a long-range correlations. Actually, what is called the correlation length will diverge, and we will have that the fact that the system is behaving in a collective way. It's called collective behavior, in the sense that this microscopic degrees of freedom are somehow talking with each other on long scales, and therefore the whole system behave, let's say, in a unique way. Okay, in this respect. Okay, so in the last few minutes, let me just introduce the last topic. Now, we'll see next time. I think I will spend maybe something about this and then maybe universality. I'm not sure how long I will go into. And then the plan is for the last 2 hours actually to say something about Langevin equation, unless you have seen this in other classes, or random walk or Brownian motion. Ecco, cose tipo equazione di diffusione, dinamica, equazioni di Langevin, queste non le avete?
No, nessun corso.
Ok, so, il piano potrebbe essere le ultime 2 ore che vi racconto un pochettino di dinamica, cioè di meccanica statistica fuori dall'equilibrio, e in particolare credo che faremo random walk, che insomma è un classicone, e penso che riusciremo, spero, a fare la relazione di Einstein tra il coefficiente di diffusione e la mobility.
Vabbè, adesso vediamo quello che riusciamo a fare. Okay, so the last part is the Landau-Ginzburg theory. So always about second order meaning critical points. When I talk about second order phase transition, I mean the critical point. So this is a phenomenological theory that basically we will use just for one reason, to compute to introduce the concept of correlation length and to see why the correlation length has a divergent behavior at the critical point. That's the only reason for which I'm doing that. And to introduce at least, just to mention them, to the two other critical exponents that are present in the theory of critical phenomena. So this is a phenomenological model that is basically starts from the empirical, let's say, fact that different systems are behaving close to the critical point in a very similar way, at least from the qualitative point of view. So if I describe the system in terms of deviation of temperature with respect to the critical temperature, so T minus Tc divided by Tc, or P minus Pc divided by Pc and V, etc. I get that the different system behave in a similar way. We saw the example of the Ising and the van der Waals gas. So that's why Landau-Ginzburg thought it was useful to somehow construct a theory which has as input the order parameter. So this quantity, and in the Ising is the magnetization, but it could be in general any other thing. For instance, in superconductivity, the order parameter is what is called pair condensate, so the energy gap associated with the formation of Cooper pairs, and there are other order parameters in other kind of phase transition. And to write out a theory, to write down a theory of the order parameter, and study this theory, use this theory of the order parameter close to the critical point. Okay, so this is more or less the idea. Now, as I said before, the order parameter could be a scalar, but it could be also a vector. If you have a model, not an Ising model, but an Heisenberg model, for instance, you have the magnetization, you can have whatever direction in space. So in that case, it's not a scalar, but it is a vector. But here, we will just consider a scalar. So we will introduce a field. So we are in d dimension, first of all. So d could be 2, 3, 1, it could be also fractional in principle. And this happens when you have interaction, you have a normal dimension. Yeah, we introduce phi as a function of x, which is the order parameter. Okay, that tells you is a quantity that basically tells you if you are above or below the critical point, depending on the fact that this quantity has a finite value equal to 0. In that case, you are above the critical point. If this quantity has a finite value different from 0, then you are below the critical point, and you have this second order phase transition. Okay, but what is important in this theory is the behavior close to the critical point. Now, one thing that one introduce is a functional of phi that is written as in these terms. Okay, so I will write first, and then I will comment, and then I think I'll close with this. Now, x is a vector in d dimension, so I will not put a vector here,
but it's meant to be a vector in d dimension. Okay, and is defined is a functional. Is defined as an integral over a space dxd of this quantity epsilon squared divided by 2, the gradient of p modulus squared plus a potential minus h of x times p of x. And let me close. Now, this this functional. What does it mean functional? It means that this integral is a function of the function, of course, that you have here. Okay, so if you change the field, this is a field p of x, you will change also this functional. Okay. Let me conclude just by saying that what basically one is doing here is a sort of coarse graining in the sense that in the Ising model, for instance, we have a discrete positions of the spin space, and we are computing the magnetization, for instance, the average magnetization over these discrete points. Whereas here we are using a continuous limit. We are doing a continuous limit and using a field, which is this phi. Okay, that somehow has the meaning of averaging over the microscopic degrees of freedom and defines for each point in space a field which is this object parameter, which somehow averages over the microscopic degrees of freedom that I will not even see in this theory. So I will somehow remove the microscopic degrees of freedom and work directly in terms of a field that, in the case of the Ising model, would be the magnetization, but in general, it's a field that is called object parameter, and which is somehow averaging over the microscopic degrees of freedom. Okay? And I will stop here and continuiamo direi martedì, sì, sono le 11. Grazie, arrivederci.
Arrivederci, grazie a lei.
Arrivederci.
Ciao. Ciao.
Arrivederci.